Welcome to the third video on special relativity, this one looking at length contraction. And in this video we're going to say what we mean by length contraction and show how to carry calculations to work out the contracted length. Well, one of the consequences of Einstein's postulate that the speed of light is constant is that if the speed of light is constant, then objects that are moving very fast are shortened or contracted in length. So length contraction is the shortening of objects that are traveling at fast speeds. And we can work out what the length contraction is. The length contraction, so the contracted length L dash is equal to the actual length times the square root of 1 minus v squared divided by c squared. Let's have a look at what this might mean. So if we've got a rocket that is traveling from Earth to our second closest star, Proxima Centauri, which is 4.2 light years away, and we managed to be able to travel at 0.8 times the speed of light, we can calculate the length of the journey according to the pilot of the rocket. Okay, so the length of the journey according to us stationary on Earth would be 4.2 light years, but the length of the journey according to the pilot of the rocket, because they are moving at 80% of the speed of light, would be 1 minus 0.8 squared divided by 1 squared, so 1 minus 0.8 squared, square rooted times the 4.2 gives us 2.5 light years. So from the point of view of the moving observer, moving in the rocket, the length is contracted from 4.2 light years to 2.5 light years. A rocket is measured at 500 meters on the launch pad on the Earth. Calculate the length of the rocket the pilot measures during the journey. Calculate the length of the rocket the observer on Earth would make if the ship was moving at 0.8 times the speed of light. So the length that the pilot would measure, well, it's moving relative to them and the pilot is stationary relative to them, so it appears to them to be the 500 meters that it has always been. In the same way that the clock on the rocket appears to them to be doing the same thing as it was before, it's only from the point of view of a stationary observer that it appears to be different. So calculating the length at 0.8 times the speed of light, now it's moving, so the length is contracted, and we can substitute in our values, and so it appears to an observer, stationary observer watching this moving rocket traveling at 80% of the speed of light, that it has contracted in length to 300 meters long. Okay, this can lead to a number of paradoxes that aren't really paradoxes, but if we have a train that's just longer than a tunnel, if it's traveling at a high speed, does the length contract to mean from a stationary perspective it fits in the tunnel? But from the train's point of view, the tunnel gets shorter as it moves towards the train. Something called simultaneity means that from the point of view of the observer, it does fit. From the point of view of the train, both the front and the back aren't in the tunnel at the same time. You can Google and see lots of videos about this. From the point of view of higher physics, don't worry about it. So from the point of view of higher physics, you need to know what is meant by length contraction, the shortening of length to a stationary observer of an object that is moving at large speeds. And you need to be able to use the relationship to work out the length contraction.